All right, here's our final example. So a kilogram block on an incline of 20 degrees, and it's attached by a rope to a free hanging block of 5 kilograms. Now, assuming that they're both frictionless and the rope and the pulley are massless, what's the acceleration of the blocks? So first, and what's the tension in the rope? So as we did before, we're going to want to look at this as a system. I think it'll be a lot easier to do as a system, so that's the way we're going to do it, although we could break it into the tensions and the gravities experienced by both blocks. So this one doesn't have any force normal operating on it. It's just going to have the force of gravity, which in its case is going to be equal to 5 times 9.8, which is equal to 49 newtons. How much gravity does this one have operating on it? Well, its force of gravity is going to be equal to 10 times 9.8, or 98 newtons. So if we want to break this into its perpendicular and its parallel component, then here's our angle of 20 degrees. So here we're going to have cosine of 20 times the force of gravity. So force of gravity perpendicular, what will be canceled out by the normal force. Force of gravity perpendicular is going to be cosine of 20 times that 98 newtons, which is equal to 33.5 newtons. Oh, whoops, sorry, I accidentally gave you the wrong one there. That's what the other one's going to be. In fact, we don't have to care what this one is yet. Cosine 20 force gravity, it's a number. It is a number, but we also know that the force normal, the normal force, is going to be equal to the force of gravity perpendicular. So these two things here, they're equal to one another, but they get canceled out. The force of gravity perpendicular and the force of normal, the normal force, are going to cancel one another out. So we don't have to worry about what they are. All we have to worry about is what the parallel is, because there'll be no acceleration perpendicular to the surface of the triangle, because we know that they're going to get canceled out because of the way the normal force works. So all we care about is how much is parallel. How much is parallel? Well, that's going to be sine 20 times force of gravity. So force of gravity parallel is going to be equal to sine 20 times the force of gravity, which this one is 33.5 newtons. So we've got the amount parallel, and we've got this amount here. Like before, we're going to consider this as the positive direction. So positive turns around, turns the corner, goes down. We're going to consider it the same as we did in the last lesson where we worked on a problem similar to this. So that's all that we have. The only thing left that we haven't really talked about is we've got these tensions working in the rope, right? But if we look at the system as a whole, then the only things pulling in an external fashion are the two forces of gravity, the parallel and the fully parallel, the one that's going completely down. So the tensions are actually going to be canceled out when we look at it as a system, because the rope is going to stay taut the entire time, so we can consider it to be a rigidly moving system where the accelerations are going to be the same. If you haven't worked on a problem like this before, you should really go back one lesson and look at the final example for that one, because it's very similar. We're just throwing in the incline to make things a little bit more difficult. All right, so moving on, now we know what our forces are. Really, the only two forces we have to care about are the force of gravity for this one is going to be equal to 49 newtons. We want to find out what's the acceleration and what's the tension in that rope. And then this one is going to have the force of gravity parallel for its force of gravity, which is going to be 33.5 newtons. So what's the mass over here? This is a mass of 10 kilograms. This is a mass of 5 kilograms. So what's the forces acting on the system? If this is the positive direction, then we've got F net for the system is equal to the mass of the system times the acceleration. And we know that they're going to have the same acceleration because they're connected by that rope. They're going to, if one moves, the other one has to move the same amount. So we can use the same A for the two of them. So F net system, we've got 49 minus 33.5 newtons for both of them is equal to, both of them summed together, 10 plus 5 times A, We start doing some simple math. We get 15.5 is equal to 15 times acceleration. We divide and we get 1.03 is equal to the acceleration, like this. So there's going to be an acceleration this way and an acceleration this way. For this one, it's going to be going directly down. For the smaller block, it's going to go directly down. And for the larger block, it's going to move parallel and up the surface of the triangle. And they're both going to be at 1.03 meters per second per second. Now, what's the tension got to be? For this, we'll look at just a free body diagram. So let's consider the smaller one. It has some tension, T, and it has some force gravity pulling down. We know what the force of gravity already is. It's 49 newtons. What's that tension? We don't know that, but we do know that it has an acceleration equal to 1.03, and we know its mass is equal to 5 kilograms. So we put all of these things together, and we're finally able to figure out what it is. We've got that the net forces is equal to the mass times the acceleration. So we've got Fg, because that's the positive direction, minus T is equal to 5 times 1.03. So 49 minus 5 times 1.03 equals the tension. So the tension is equal to 43.85 newtons, which makes a lot of sense because if things are going to actually if the block is going to be able to fall, there's going to need to be slightly less tension in the rope because it has to have a net force that is stronger downwards than upwards. Otherwise, it won't accelerate down, it'll accelerate up. All right, that finishes it for this lesson. I hope you enjoyed it, I hope you learned something, and we'll see you at Educator.com for the next lesson.